So before we talk about the linear ODEs, right now we will trying to see how about the nonlinear ODE, which means the coefficient will have the function of y. Okay, so um, non-linear ODE with BVP, and we will try to solve with both the shooting method and the finite difference. Let's see how that differentiate with our previous linear ODE. Okay. We will have an example which is y double prime plus 3x 1 plus 0.2y y prime plus 7y equals to cosine 2x. So you can see that forcing function is only as function of x. The coefficient for y is 7. The coefficient for y double prime is constant. So those are fine. But the only difference is that for the y prime, the coefficient has the contribution of the y part. That means this ODE is not linear anymore. It's become a nonlinear ODE. Then for the finite difference, for the finite difference method, it's very similar as what we learned from the linear ODE, okay? So it's still, first we will do the discretization, which means that we will separate our x domain into n different points, which h will be x final minus x0 divided by n. And if we have, let's see, if our boundary condition is y0 equals to 1, y pi equals to 0. So these are the boundary conditions with 2 points. And what we know that our x domain is from 0 to pi with n points. So our unknown will be from y1, y2 until yn minus 1. Because our y unknown, y0 is known. So we have those unknown y1 to yn minus 1, those finite nodes. Okay, and we can try to write our y double prime equals to, trying to write our derivative with algebra equations, okay, using finite, central finite approximation. So y double prime equals to negative 3x 1 plus 0.2 y prime minus 7y plus cosine 2x. Okay, and our coefficient for y, so y double prime can also equals to fi minus 1 minus 2 fi plus fi plus 1 divided by h squared. That is the central difference. Y prime equals to fi plus 1 minus fi minus 1 divided by 2h. Combined with these two equations, we can write the coefficients of our y. So it will be 1 plus h over 2 pi yi minus 1 minus 2 plus qih squared yi plus 1 minus h over 2 pi yi plus 1 equals to h squared ri. So this is very similar to what we have been derived from the linear ODE. So this is ai, bi, and ci, okay? ai, bi, and ci. Then this is the b matrices, bi, okay? Then the pi is from our initial conditions is 3xi 1 plus 0.2yi. The qi is equals to negative 7. The ri is cosine 2xi, right? So the only difference is this pi is not only as function of x, it also have the function of the y part. Then it comes to the difference. We can still construct our a y equals to b. But the difference between the linear and the nonlinear is for the nonlinear, the A matrices is only as function of x. So you can know what is the A matrix, the coefficient. But for the nonlinear part, it will have some contribution from this yi. So unless you know what is your y matrices, you don't know what is the A. Then you couldn't solve these equations for the finite difference method. Then what we need to do is give an initial guess of y, which is called by ODE. So you can give by ODE as your initial guess. Then you will know what is the PI, QI, RI. You will know what is the coefficient AI, BI, CI. Then you can construct this AY equals to B. Then you solve it. So get the coefficient matrices, coefficient matrix, AI, BI, CI, which construct A and B. So you based on the y-old, you can get this A matrices and B. And you can get the y new, which is A divided by B. Okay, so A divided by B. And to solve this y new, and you can do the arrow check, which is compare your y new and y old. So if the y new and y old are exactly the same, or the difference is within the tolerance, that means you are done. You get exactly what you need to get for the solutions y1 to yn minus 1. But usually the first initial guess won't be accurate enough. So you need to do the iterations. You update the y old with y new and do one more case until the maximum error will be smaller than the tolerance. And when they say the maximum error means the comparison between the y new and y old, all those numbers inside y, it can be y1, y2 until yn minus 1. All of those difference will be smaller than the tolerance, then you are done. Okay, so this is the difference between the nonlinear ODE with the boundary value conditions as compared to the linear one. The linear one you directly can solve, which is A over B. But for the nonlinear, you need to update y until you meet all the errors smaller than the tolerance. Well, for the shooting method, for the non-linear BVP, the shooting method, it's the same. It's the same methodology. You use the iteration method. You guess the initial conditions until the initial conditions meet for the boundary conditions. But compared to the linear one, it's just a longer or larger number of iteration you may need to do, and it's also sensitive for the initial guess. So for the nonlinear BVP, you may have multiple solutions, and how you choose those solutions, it will be means different initial guess will lead to different solutions. So you will choose the one with the right physics. Okay, so for nonlinear BVP, it may have different solutions, and based on different initial guess, you can have X as negative range or positive range. You will get different solutions. You will choose the one based on your physical models with the right physics. And for the finite difference, basically you give a y old and you update the y new with A over B, that solutions, and you will find as compared the y old and y new until all the y values inside your y solutions have the same, have the small arrow as compared to the tolerance, then you are done. So that is how we solve the nonlinear ODE with the BVP using this different numerical solutions. Okay.